This video is a review of bonding basics. All of this material is covered in a Chem 1 course. Chemical processes always involve compounds. Compounds are formed by chemically binding together multiple atoms or ions. These bonds involve only the valence electrons. Recall that valence electrons are those electrons in the outermost principal energy level. For the representative elements, the group number is also the number of valence electrons. The most common symbol form that chemists use when discussing bonding is called Lewis symbols or Lewis structures. This shows the valence electrons as dots arranged around the atomic symbol. For example, how many valence electrons does a hydrogen atom have? 1. So the Lewis symbol for hydrogen is an H with 1 dot beside it. The dot can be on the top, the bottom, or either side. What is the Lewis symbol for sodium? Na with 1 dot. What about chlorine? Chlorine is in column 7, so its symbol is Cl with 7 dots around it. Notice that we put a maximum of 2 dots on any side of a symbol. When bonding, most atoms follow the octet rule, which states that atoms will gain, lose, or share electrons until they have 8 valence electrons. An exception to that is hydrogen. Because hydrogen has only the very small first principal energy level, it needs only 2 valence electrons to be satisfied. Let's look first at ionic compounds. What happens between a sodium atom and a chlorine atom for these to form the compound sodium chloride? Sodium, with 1 valence electron, is willing to give that electron away because its next energy level down is full. At the same time, chlorine has 7 valence electrons and would like to gain 1 electron to fill up its outermost level. So sodium donates its 1 electron to chlorine. As a result, sodium is now positively charged and chlorine is negatively charged, and those two oppositely charged ions attract each other and stick together. That's what an ionic compound is. Oppositely charged ions sticking together. Another way ionic bonding is sometimes illustrated is like a chemical reaction. An Na and a Cl react to form NaCl. This notation is showing the positive sodium ion and the negative chloride ion, and they are attracted together again because of their opposite charges. It is always true that electrons are transferred from a metal to a nonmetal to form ionic compounds. Look at 2 more examples. Draw an atom of magnesium and an atom of fluorine. Magnesium needs to give away 2 electrons. A fluorine atom can only gain 1 electron. So what happens to form the compound magnesium fluoride? This magnesium can only give 1 electron to this fluorine. That doesn't make the magnesium atom stable. It still needs to give away another electron, which means we need to draw another fluorine. It takes 2 fluorine atoms for every 1 magnesium atom to make this compound. Of course, we knew that already from our knowledge of nomenclature rules. How do aluminum and oxygen atoms combine? Aluminum transfers 2 electrons to this oxygen. That oxygen atom is now stable, but aluminum needs to give away another electron still. So we draw another oxygen atom. Aluminum gives its remaining valence electron to this oxygen, making the aluminum stable. But now this second oxygen needs to gain 1 more electron. So we draw another aluminum to provide that electron. Now, we need 1 more oxygen atom. Now all the atoms involved are stable. It takes 2 aluminums and 3 oxygens for all the atoms involved to be stable ions. We know that Al2O3 is the correct formula for aluminum oxide. This illustration shows us why. Ionic compounds consist of ions sticking together because they have opposite charges. This is a strong attraction. Because it's a strong attraction, ionic compounds have relatively high melting and boiling points. You have to put in a lot of energy to weaken and break the ionic attractions. Once you do melt an ionic compound, those ions can move around in the liquid. Also, when you dissolve an ionic compound, water, being a polar molecule, is able to separate the ions from one another, so the ions, again, can move around. If the ions can move, that material can conduct an electric current. So molten and aqueous ionic compounds conduct electricity. Ionic compounds do not conduct electricity as solids, because the ions are held rigidly in place in the solid form. When ionic compounds form, it's not just 1 positive and 1 negative ion, or 1 positive and 2 negatives if that's the ratio. It's not just one combination. The formula we write for an ionic compound shows us the lowest ratio of the ions, but in an actual sample, you have ions attracting on all sides. You have a lattice of positive and negative ions. Imagine layer on top of layer on top of layer, beside of a layer of positives and negatives. The stability of an ionic compound is measured by its lattice energy. I will cover lattice energy in another video. A quick side note here about electron configurations for ions. The electron configuration for an ion should accurately reflect the gain or loss of electrons that has occurred to make the atom become the ion. For example, for a sodium atom to become a sodium ion, it loses 1 electron. If you look at the electron configuration for the sodium atom, what electron is lost? The valence electron, as always. So the electron configuration for the sodium ion will not have 3s1 on the end, because this electron has been given away The electron configuration for the sodium ion then is 1s2, 2s2, 2p6. Notice that this matches the electron configuration of a noble gas. A noble gas electron configuration is a very stable electron configuration, and this is the entire reason sodium gives away its valence electron. So it can now have a very stable electron configuration. What's the electron configuration for a chloride ion? What happens to a chlorine atom to become a chloride ion? This time the atom gains one electron. Compared to the electron configuration of the atom, the electron configuration for the ion should show one more electron. This additional electron fills up that last principal energy level of chlorine. That's why chlorine gains an electron. It's more stable as a -1 ion because now its valence shell is full. One more. What is the electron configuration of a calcium ion? What happens to the calcium atom to become a +2 ion? The atom loses 2 electrons. Which 2? The 2 valence electrons. The electron configuration for the calcium ion then is 1s2, 2s2, 2p6, 3s2, 3p6. These last 2 examples effectively illustrate the term isoelectronic. This word refers to different objects with the same electron configurations, like the chloride ion, the calcium ion, and the element argon. If they have the same electron configurations, why aren't they the same thing altogether? Because they still have a different number of protons in the nucleus. The chloride ion has 17 protons. The calcium ion has 20 protons. The argon atom has 18 protons. They're still different substances. It's just that their electron configurations match. Moving on to molecular compounds, the simplest of which is a hydrogen molecule. When one hydrogen atom is close to another hydrogen, it gives that second hydrogen access to its electron. The second hydrogen does likewise. This shared pair of electrons constitutes a covalent bond. Covalent bonding is what holds non-metal atoms together into a molecular compound. Non-metal atoms cannot transfer electrons to one another, like we saw in ionic compounds. Both nonmetals would want to gain electrons. Neither nonmetal is willing to give away electrons. So a covalent bond is shared electrons. We again use Lewis structures when representing covalent bonding. A valid Lewis structure should show an octet of electrons around each atom, except for hydrogen, which stops at 2 valence electrons. When 2 hydrogen atoms bond together, as we discussed on the previous slide, each hydrogen atom shares its electron with the other hydrogen, resulting in a covalent bond between the 2 atoms. We draw a bonding pair of electrons as a bar between the 2 atoms. A bar in a Lewis structure then represents 2 electrons that are shared by both atoms. When 2 chlorines bond together, they don't need to share all of their electrons with each other. Each chlorine only needs 1 more electron to have a full valence shell. So each chlorine shares 1 electron with the other. In a chlorine molecule, there is 1 pair of bonding electrons, which is also called a shared pair, and many pairs of non-bonding electrons. These are also called unshared pairs. Two atoms can share more than one pair of electrons between them. Atoms can share 4 electrons, or 2 pairs, to form a double bond. In an oxygen molecule, the oxygens share 2 pairs of electrons. Remembering that atoms are stable when they have 8 valence electrons, is this oxygen on the right stable? Yes, it has access to the 4 shared electrons plus 4 of its own electrons, totaling 8. The same goes for the oxygen on the left. Atoms can share up to 6 electrons. This is called a triple bond. This happens in a nitrogen molecule. Each nitrogen has access to 6 shared electrons and 1 unshared pair, again totaling 8 valence electrons for each nitrogen. To draw your own Lewis structures, you need to follow this set of steps. Follow these in this order and you will correctly draw a Lewis structure for any molecular compound. Let's look at a few examples. Nitrogen trifluoride. First, sum the valence electrons. Nitrogen brings in 5 valence electrons, plus 7 from a fluorine times 3 fluorines is a total of 26 valence electrons. Draw a skeleton structure. Put the single atom of nitrogen in the middle and attach the fluorines around it with single bonds. Complete the octets of the outer atoms. Put 6 unshared electrons on each fluorine. Do we have electrons remaining? Well, how many electrons are currently in our drawing? That's 24. Remember that each line represents 2 electrons. There's a total of 24 electrons in our picture. We're supposed to draw 26 according to our total. We have 2 more electrons to place, so we add them to the central atom. We've drawn the proper number of electrons. Now the question is, do all the atoms have an octet? The answer is yes. This, then, is the complete Lewis structure for NF3. Look at CCl4. Sum the valence electrons, 4 from carbon, 7 from each chlorine times 4 chlorines, equals 32 valence electrons. Put carbon in the middle. Chlorines around it, attached by single bonds. Then fill the octets of the outer atoms. Once you fill the outer atoms, look to see if you have drawn all your electrons. Count the number in your picture, compare it to the number that you're supposed to have. There's 32 electrons in our picture, 32 is our total. Then check to see if all atoms have an octet. All of these do, so again, we're done. Let's look at H2O. Each hydrogen has 1 valence electron times 2 hydrogens present, plus 6 electrons from oxygen, for a total of 8 valence electrons for this picture. Oxygen goes in the middle. Fill the octets of your outer atoms. Your outer atoms this time are hydrogen. Hydrogens are full with 2 electrons, so those hydrogens are already full. As soon as hydrogen has a bond, it's done. We still have electrons to draw. We have 4 in our picture. We need 4 more. So we put those 4 electrons on the oxygen atom. Let's do just a couple more examples. Sulfur dioxide. The number of valence electrons is 6, plus 6 times 2, for a total of 18. The skeleton structure shows sulfur in the middle. Complete the octets of the outside atoms. Do we have electrons left to draw? Yep. We need to place 2 electrons on the central sulfur atom. We have all our electrons drawn now. Do all the atoms have 8 valence electrons? No. Sulfur is still short. So we can't draw any more electrons on it. We don't have any more electrons to draw. That means we need to rearrange the electrons we have. Pick either oxygen and remove a pair of what are now unshared electrons. Make it a shared pair instead. The oxygen still has access to these electrons, but now sulfur also has access to them. Is there any reason we could not have selected the other oxygen? Is there anything wrong with that Lewis structure? There definitely is not anything wrong with that Lewis structure. In fact, both Lewis structures are equally valid. Often scientists will draw both. This is the idea of resonance. Multiple correct Lewis structures for the same compound. Sulfur dioxide in reality is actually a mix of these 2 drawings. The real sulfur dioxide molecule is not either one of these individually. It's as if we could blend our 2 drawings together into a single object. One more example, the chlorite ion. First, sum the valence electrons. Chlorine brings in 7, plus 6 from each oxygen. We also have to account for the negative charge on the ion. A negative charge means that the ion has that many more negative electrons. So we need to add 1 to our total here. That gives us 26 electrons to use. Now draw the skeleton structure. Chlorine in the middle with oxygens attached by single bonds. Fill the octets of the outer atoms. Once the outer atoms are full, look to see if you have any remaining electrons to draw. This time we do. We need 2 more electrons, so we place them on the chlorine atom. All our electrons are drawn now. Are all the atoms satisfied with 8 valence electrons? Yes. The only thing we have left to do here is we need to mark in our drawing that this is a charged ion by putting it in large brackets and writing the charge on the outside. The last thing for this video is metallic bonding, which actually is a bad name. This is not a way for one metal to bond to another. That doesn't happen at all. Metallic bonding is actually the force that holds the atoms of a metal together. In a copper wire, in gold or silver jewelry, in a brass musical instrument, this force is what holds the particles together. This exists both in pure metals and metal alloys. In a metal sample, the metal atoms actually release their valence electrons to be shared all throughout the sample, shared by all the metal cations. This is most often described as metal cations in a sea of mobile valence electrons. As a result of this structure, metals are good conductors of electricity. Because the freed valence electrons are mobile, they can move. They can conduct electricity down the line. Metals are also malleable and ductile. This sea of valence electrons acts like packing peanuts. The metal cations can slide around past each other, meaning the metal reshapes rather than breaking. Metals have high melting points because, much like we discussed with ionic compounds, the attraction between these positive metal cations and all these negative electrons is a very strong attraction. It requires a lot of energy to weaken and break that attraction. And lastly, metals are known to be lustrous, which is just a fancy word for shiny.